Hi everyone. Today what we're going to do is we're going to add in another identity. And so we're going to build on the 7 that we worked on previously. And then we're going to spend some time working to see why these things are useful, how we can use them. And then we're going to play around with a few applications. So you see, notice the title for today, we're talking about angle identities, day 2. So we should have all 7 from previous lesson as well as our 2 grade 11 identities in our back pocket, and we're going to begin to build. So the first thing I want you to notice is that we're going to prove a new identity for today. So when you look on the screen, there is your sine compound angle identity. You'll notice that sine A plus B is going to equal sine A cos B plus cos A sine B. Now, we have to go through the process of trying to prove that. So, what we need to draw on is everything that we have in our disposal. Now, normally I would say let's play around with this for a few minutes. However, given kind of the context and the situation we're in, I think we might just kind of lead you through this proof. So, for us to break it down, what we have to try to do is ask ourselves, well, what tools do we have at our disposal? And when I look at this compound angle, the only tool that I have at my disposal is a cos compound angle identity. So if I was somehow able to change this sine identity into a cos identity, then maybe I could use that. And luckily, I have a way to be able to break that down. Recall from yesterday that I also have my complementary angle identities that would say that the sine of any angle is equal to the cos of pi by 2 minus that angle. And so what I can do is I can take this sine compound angle and I can turn it into a cosine using my complementary angle identity. So that allows me to then say that the left side, which was sine A plus B, could be written as the cos of pi by 2 minus that angle. And there is me applying that blue complementary angle identity. Well, now that I have that, I could break that down the way it's written. However, we would notice that we would run in a big circle. So instead, what I can do is I can simplify the inside. I notice that I am subtracting this whole bracket, so I can expand those brackets in a way. And now what I can do is when I look on the inside, I actually have 3 angles. But what I can do is I can kind of group it and think of pi by 2 minus A as one angle, and then think of B as my other angle, and that's what allows me to then use my cos compound angle identity from the last lesson. So I'm going to break down that lesson, and we should have that green compound angle identity known off by heart. What is it? It's the cos of the first angle, cos of the second angle, opposite sign in between, sine of the first angle, sine of the second angle. And now that we have that, we can start to try to manipulate that, still with the goal in mind to make this left side look like the right side. Now, when I scan the right side of that identity, I notice that all I have are angles A and B. I don't have any of these pi by 2's in it. So my focus becomes eliminating the pi by 2. Well, this first cos compound angle identity is pi by 2 minus, and therefore I can use my complementary angle identity to replace that. I know that cos pi by 2 minus A is equal to sine of A. Simplify that down. And now when I come to my next compound angle identity, I see that my next compound angle identity, I notice that it's also a complementary angle. And I know that the sine of pi by 2 minus A is equal to the cos of that angle, cos A. And notice that we just went through and we made the left side look like the right side. And so what we have then is we have a proof for our sine compound angle identity. Now, we've added in a new identity today with our sine compound angle, but we haven't dealt with it in its entirety. So let's jump into the next sort of situation. What you'll see on the screen now is the other situation. We just dealt with sine a plus b. Now we need to make sure that we expand that identity fully to deal with sine a minus b. So I would argue that this would be one that if you had a full grasp of what we did last time, you might know where to begin with this one. So if we were to start and go through and deal with this proof, I don't know how to break down the sine of an angle subtract an angle. However, I do know how to break down the sine of an angle plus another angle. And just like when we went through and proved what cos A minus B was, we can use that same approach today. Rather than viewing it as the subtraction of two angles, I'm going to view it as adding a negative angle. Because what we just learned on the last screen, that we can break that down using that identity. It was sine of A cos of negative B plus cos of A sine of negative B. Now as we're trying to make this left side look like the right side, I notice that on the right side of my identity, I don't have any negative angles. So my motivation becomes to eliminate my negative angles. And I have two ratios with negative angles. So if I can recall back to what we dealt with last time, I know that the cos of a negative angle is equal to the cos of a positive, and I know that the sine of a negative angle is equal to the negative sine of the positive. And so by substituting in those values, then I'm almost equal to what my right side says. The only thing I need to do is to simplify that last term. If I am adding that negative product, then really what I'm doing is subtracting, and I now have my right side. And since my left side equals my right side, I have now proven that identity. And now we have our full sine compound angle identity. Let's take a look at it. And so what you'll see on the screen now are both versions of that compound angle identity. We have the positive case that we looked at on screen 1, and we have the negative case that we looked at on the previous screen. I want you to take a look at those two forms of our sine compound angle identity and notice that we can put the same language to it as what we did with our cos. If we do, we'll notice a general pattern in that. For me to break down the sine of A plus B, it is sine of the first, cos of the second, cos of the first, sine of the second. Notice that my angles A and B alternate. Notice that my ratios alternate. And notice that none of those four ratios are the same. So, since I included my sine A here, then I know that it must be the cos of A in the next term, the other ratio. And you'll notice the same pattern exists for our B's. Since I had the cos of B in this term, then I must have the sine of B in the last term. Now, notice the green highlight in between. The sine that I have between my angles is the same as the sine I have between my terms. And if you notice that pattern, then we can use that for every sine compound. Take a look at the subtraction option. So I see A minus B on the inside. So it is sine of the first, cos of the second, same sign in between as what I see, alternate them, cos of the first, sine of the second. I'm going to very quickly write down our cos options so you can see again how they differ but you can see them both side by side. When you break down your angle identity, it is cos of the first, cos of the second. So in that first terms, we had the same coses. Opposite sign in between. Sine of the first, sine of the second. And same thing for our cos negative compound angle. Cos of the first, cos of the second, opposite sine, sine of the first, sine of the second. So what we end up having then is one version of our sine, one version of our cos, and we really don't have to be overly concerned about what sign is in between. We take that into account when we build or break down each compound angle. So there you now have like your 8th new identity that we're going to deal with. And what we're going to do is we're going to stop there with adding in new identities, and let's spend some time seeing why these are useful and how we use them. So we take a look at problem 3, and I'll give you a chance to just give that a read. What we're going to do is we're going to work through problem 3 two different ways. And so what I want to do is I want to tackle problem 3 similar to what we're doing right now, which is you've never tackled a problem like this before, so let's kind of stumble our way through. So I'm going to imagine that I'm working my way through 3 the first time I ever tried a problem like this. Okay, I start to break down what's in the problem. It tells me that the sine of whatever x is has that ratio. It tells me the location of where x is, and it gives me my expression that I have to find a value for. So I need to find sine pi by 3 minus x. Okay, again, I'm stumbling. So I notice what I just circled in red, that's a compound angle. And so maybe what I do is I break down my compound angle. So I'm going to start with my sine pi by 3 minus x, and I can at least break that down using our compound angle identity. So that would be the sine of the first, cos of the second, same sign in between, cos of the first, sine of the second. And at least I can break that down in that regard. Now, I start to look back up into the problem, and here's where I'm stumbling. Well, sine of pi by 3, that's a number. And sometimes as we work our way through, what can get a little confusing is that we don't recognize the difference between what I circled in gold versus what I circled in blue. And I think it stems because in radian measure, we see a pi, and sometimes we mistake that for a variable because we see it as a symbol, and we forget that it's just a number. What I circled in gold, I can calculate. I can find the value of that. What I circled in blue, I can't because of my variable. So if I just get rid of those outlines, I can go through and I can deal with my pi by 3. So off on the side, I'm just going to put down my rotation angle. There is my pi by 3. That's a big angle, so I have my big opposite side. I know the rest of my triangle, and I can at least make that substitution. So the sine of pi by 3 is my root 3 over 2. I don't know the cos of x, so I'm going to have some bracket in there. I can calculate the cos of pi by 3, adjacent over hypotenuse, and, well, if I look back up into the original problem, what I underlined in blue gives me the value of sine x. I've been told that that's 2/5. And so maybe that's my starting point, is that I break down what I got, I see what I need to find, and then I plug in whatever I know. There's a stumbling approach. So I get to the point where I can't find the value of this because I'm still missing that cos x value. You can see it with that open bracket. So maybe now I go back and I say, okay, well, that's giving me information about angle x. So what do I know about angle x? Well, first off, what I just circled in green, I know where it's located. It tells me that I have to be greater than pi by 2, less than pi. That puts me into the second quadrant. So if I'm not particular about how I draw my terminal arm, then at the very least I can do that. Well, maybe I now go back to what I've dealt with underlined in blue. My sine x is 2/5, and so I can now drop in my altitude opposite over hypotenuse. Hey, I have two sides of a right triangle. I can find the third using Pythagorean theorem. So you can go through and you can write out your Pythagorean theorem. And so maybe you're going, your 5 squared is equal to, a squared plus 2 squared. We can see our 25 minus our 4 has to be our a squared. And so our a has to be root 21. I don't need to see any of that red Pythagorean theorem at all. If you are quite comfortable to look at that and say, hey, there's a root 21, feel free. Just make sure that we don't make a huge mistake. That's to the left. That means I have a negative adjacent side. Okay, well, now that I have that diagram, and that is what represents angle X, well, I can now find my cos ratio because it's just on my triangle. So my cos of X is going to be my adjacent side over my hypotenuse, and there we go. Now you take a look at that gold, and we can continue to stumble, but since all of those are numbers, everything we should be doing now is just reducing. Maybe we're writing down root 63 as a negative, but then we've got to reduce that. I'm hoping it's not too big of a jump for us to be able to look at that root 21 and say, well, 21 is 3 times 7. So when I go and multiply those two radicals together, I'm going to have 2 3's underneath. So maybe I can just jump straight to a minus 3 root 7 as that simplified form. That is over tenths. But notice my other fraction will be over 10. So I can just get my common denominator, since I already have one, and simply just write it that way. It'll all be over tenths minus your 2 of them. And so we can plug in our information we know, we can go through and simplify, and we now get down to an exact value for that expression. So that represents just a means for us to be able to stumble through the problem. What I want to do is I want to tackle this problem again. So you'll notice that I just have problem 3, and we're going to tackle this one again. But this approach for us is going to be the exact same approach, but in the opposite direction. We have enough experience right now that we can kind of see that we're going to need to use the sine x and its location. And so we put down a quick set of axes. We notice we're in the second quadrant. I know that I have opposite and hypotenuse, and I go on the hunt and I find that. So I have 25 minus 4. So now when I get to the point where I'm breaking down that compound angle, you already have in red the information you're going to need. Sine pi by 3, so sine of the first, cos of the second, same sign in between, cos of the first, sine of the second. Well, now when we go through and sub in, we're pretty good on the sine pi by 3, big angle, big opposite side. And now, since you've already done the work in the red, you can see cos pi by 3, sine of x, it's given. And notice, as we gain experience with this, you may already know what information you need to solve the problem, and instead of waiting till the end, you go on the hunt and you find that first. So we could finish that one off. We're good. We did it on the previous page. Okay, let's keep it moving with how we can use this stuff. So what you'll see on the screen right now is me asking you to find an exact value for cos pi by 4 plus pi by 3. And so this might be an opportunity for us to pause the video and try this problem on our own. I think we have enough in our background to maybe give it a shot. If we're still feeling a little nervous, then hang on a second and we can walk through this one together. So pause the video now if you want to give it a try. Okay, we're back. So notice the first thing is that we go through and we have two angles on the inside. Now, my first instinct may be, well, why don't I just add those two angles together? Yeah, except that's going to give me an angle with a denominator of 12. And I don't know my twelfths or my pi by 12s off by heart. So maybe then I avoid trying to go through and simplify the angle on the inside, but instead say, I know pi by 4 and pi by 3. Why don't I break down that compound angle so I can deal with those angles? So how do I break down a cos? It would be cos of the first times cos of the second, opposite sign in between, sine of the first, sine of the second. Now that we have that, we can calculate all of those because we know what the angle pi by 4 is and we know what the angle pi by 3 is. If we still need to, we may be drawing a picture and dealing with our pi by 4, and we may be drawing a picture and dealing with our pi by 3. Feel free to include them, but also feel free to challenge yourself not to have to draw the picture, but instead to try to visualize it. My cos of pi by 4 is going to be my adjacent side over my hypotenuse. My cos of pi by 3, well, pi by 3 is a big angle, which means it has a small opposite side. My sine is my 1 over root 2. And my sine of pi by 3, big angle, big opposite side. Well, now what we have is we have a fraction that maybe given our last problem, we can see we're going to have a denominator of 2 root 2 in both of those fractions. So why not just jump to writing it with the common denominator of 2 root 2 right off the bat? What's going to be the numerator of the first one? 1 times 1. What's going to be the numerator of the second one? 1 times root 3. And we come in on that line. Now we know that that's bad form because we have a radical on the denominator. So now what we can do is we can multiply that by root 2 over root 2 to rationalize that denominator. And when we expand in the root 2, we'll get root 2 on the first term, we'll get root 6 on the last term, and on the denominator, 4. And there we go. We now have an exact value for that cos compound angle. Okay, let's keep it going, getting more and more practice and building up more instinct as we go. What you see on the screen now should be an opportunity for all of us to try on our own. So I want everyone to pause the video, give this one a shot. Okay, we're back. So for us to go through that same approach, we're going to break down our compound angle. I have sine of the first, cos of the second, same sign in between, cos of the first, sine of the second. And now that we've broken it down, we recognize those are all special angles. We can go through and we can replace them with what they're equal to. The sine of pi by 6 is the smallest angle, which means we have the small opposite side. I've got cos of pi by 4. That one's pretty straightforward. Pi by 6 has a small angle, so small opposite side, so it has a large adjacent side. And then the sine of. Now that we get to that point, we can see that we're going to have a common denominator of 2 root 2. My numerator on the first fraction is 1, and root 3 on the second fraction. Now I can rationalize it by multiplying top and bottom both by root 2. And there we go. So notice we get something pretty similar. Okay, hopefully we're starting to build a little bit of confidence. We're feeling more comfortable to go through and sub in our values for our special angles and break down our compound angles. Okay. Now we come to a point where maybe we're going to hit a wall a little bit. I've asked you to determine the exact value of cos 5 pi by 12. And in question B, I want you to give me the exact value of sine pi by 12. And so as we examine both those angles, we may say, but wait a second, I don't know pi by 12. That's not a special angle. And perhaps something that we did earlier might guide you towards what you could try. If we're absolutely stumped, then what I would want you to do is just maybe take 5 pi by 12 and turn that into degrees. And I want you to think about what that angle would be in degrees. On a quick calculation for us to change that into degrees, we should see that we're talking about 75 degrees. And maybe because we now know that 5 pi by 12 is 75 degrees, that may guide us or guide our instinct to want to try something. I want you to notice that 75 degrees could be broken up into 45 degrees plus 30 degrees. And if I was to ask you what is the cos of that, well, then you should have the means to be able to go through and find it. So I'm going to get rid of all of that yellow. And now let's go back and revisit the original expression. We have to come up with the cos of 5 pi by 12. And so what I want to do is I want to break up 5 pi by 12 into two fractions, if possible, where they're both special angles. So I could then look at that and say, like, well, why don't I take a 4 pi by 12 plus a 1 pi by 12? I know that when I break that up, 4 twelfths plus 1 twelfth is 5 twelfths, so my blue expression is equal. And notice that when I reduce 4 pi by 12, I get a pi by 3, which is a special angle. Nice. However, I'm still stuck with this pi by 12, and that one is not a special angle. It doesn't become very useful. So that last approach of trying to be able to break that down really didn't work well. However, there is another way for us to get 5 twelfths. Maybe we view it as 3 twelfths plus 2 twelfths. Notice that if we added those two fractions together, we would still get our 5 pi by 12. And when we reduce it, both of those turn into special angles. Okay, I think everybody should be good to pause the video right now and finish this one off. Okay, we're back. And so I'm going to break that one down pretty quick. Cos of the first, cos of the second, opposite sine, sine of the first, sine of the second. Now that we have them all broken down, let's substitute in our values. So we know we got 1 over root 2 for cos pi by 4. Pi by 6 is a small angle, so it has a big adjacent side. I've got my 1 over root 2. Pi by 6 is a small angle, so it has a small opposite side. We can then calculate that and then rationalize it. And there we go. Now, one big idea for us, and I hope that this is really important for us, is can we take a look at B for a second and tell me how big in degrees is pi by 12? If we're okay that becomes a 15-degree angle, then maybe we can take a look back at A and we can notice that what we've just learned is how to come up with the exact value for all 15-degree angles and multiples of 15-degree angles. That coming out of grade 11 and into the first bit of grade 12, we really only dealt with special angles of 30 degrees, 45 degrees, 60 degrees, and then any angles that put you on an axis. Now, we can deal with 15-degree multiples. That's what pi by 12s are. And we're now expanding what we can come up with for exact values. So if there was anybody coming out of grade 11 or this beginning part of grade 12 that was kind of like, you keep telling us that we can deal with trig without a calculator, but it only seems that we can deal with trig for these particular angles, not all angles. Maybe you can start to see how we can expand trigonometry to dealing with exact values rather than approximates. So let's jump in then and let's play around with B. So if you're feeling comfortable, let's pause the video. Otherwise, we're working our way through this one together. So let's start it off thinking about how can we get angle break apart 1/12. Well, for me to get 1/12, perhaps I kind of look at the previous one and I said, I'm going to deal with 3/12 minus 2/12. That would give me it. And if you went with that one, great. What I want you to do is I want you to finish that one off. Don't change it. But what I want to do is maybe address it a little bit differently, just for variety. That I may have had some other people that said, well, maybe it's 4/12 minus 3/12. So I'm going to deal with it that way because when I reduce, that would be a pi by 3 minus pi by 4. And if you tackled it the other way, then this gives us a good opportunity to match up in the end. So if I'm going to break down my sine compound angle identity, it's sine of the first, cos of the second, same sign in between, cos of the first, sine of the second. Now that I've got that, I can sub in my values. Sine is a big opposite. That pi by 2 for a big opposite side means a small adjacent side. And now I can simplify. And now I can rationalize. And there we go. So for anybody who's kind of working their way through and is like, yeah, but I seem to keep getting like the same sort of expression over and over again. Like they all look the same. They've got a √6, a √2, and a 4. And in this particular case, I get the exact same thing. Nobody should be overly surprised by that. Every time you were solving for your exact values for pi by 4s or pi by 3s or pi by 6s, we all got the same looking expression all the time. It was always 1 over √2s, it was 1/2, or it was √3/2. So the fact that now for pi by 12s, we're getting similar expressions should make sense. Okay, if you're feeling brave, then everybody should be able to jump into C. Pause the video now. We'll see if we match up. Okay, we're back. So if I was to work my way through, I now need to figure out a way that I can break down 11 pi by 12. Well, I could start to look at that and say, like, I need two fractions in 12ths that are going to add together to give me 11 that would both be special angles. And maybe I think of 9 and 2. Just some other options, though. I could have had a bunch of people that would have viewed 11 as maybe 8 and 3. Notice that if we reduce both of those fractions, we get special angles. But maybe you even did something like this, and you said, well, what about 4 of them plus 4 of them plus 3 of them? That gives me 11. And before anybody goes, but why would you ever do that? There are going to be some times where it's important for us to be able to break down the addition of 3 angles. We might be able to see then how we start to expand things so that they're more than just 12ths. Okay, I'm going to now ignore these and just deal with the blue, but again, we have a great opportunity. If you tackled either one of those other options, or any of the other options that would get us 11 pi by 12, let's see if we match up in the end. By breaking it down that way, this is where I would then have a 3 pi by 4 plus a pi by 6. There's my confirmation. They're both special angles. So now I can break that down using my compound angle identity. It's cos of the first, cos of the second, opposite sign in between, sine of the first, sine of the second. And one warning I'd like to give you is that when you happen to have an angle like 3 pi by 4 that is not in the first quadrant, I would suggest putting down a quick sketch. The last few problems, I've tried to motivate you to not put down sketches for your special angles, your pi by 3, pi by 4, pi by 6, that we should be able to build those ratios without seeing the picture. However, when we start to address a 3 pi by 4, we know that we have a pi by 4 related acute angle. There are fewer people who are going to make the mistake of using that and telling me that that ratio is 1 over root 2. That when we draw the picture, we tend to find our mistake. Not always, but mostly. You can maybe see the thing that I've left off, that because I'm not in the first quadrant anymore, that negative, that would be the one that we want to focus in on. That when I draw my picture, I don't make the mistake of forgetting my directional symbols. Or at least I tend not to. And so when I sub in my cos, I'll tend to ensure that in this case, I apply that negative. For any angles in the first quadrant, I should be good to not need my picture. But again, feel free to write it down or draw one if you need to. We now get to this point where I can reduce, and now we can rationalize. And there we go. So today's topic was an ability to introduce now our sine compound angle identity, but also for us to be able to see how we can use this stuff to start to expand our nature of exact values when we deal with trig ratios. Okay, your job now, jump in on your weekly schedule and get some practice. Good luck.